In this work, we developed theory for volumetric representations of opaque solid objects. Since the 1950s, volume rendering techniques have been commonplace in graphics and applied physics as a methodology to efficiently simulate light transport in translucent media like clouds, smoke, or tissue. In the past 5 years, however, these same volume rendering techniques have become commonplace for opaque solid objects which bear little resemblance to the translucent materials for which volume rendering was originally developed. Why can we use the same volume rendering model for both a cloud and a Lego truck? We answer this question by developing a stochastic geometric theory for opaque solids. Our theory not only explains existing surface reconstruction pipelines such as NUS or VolSDF, but also helps greatly improve reconstruction performance with only small changes in these pipelines. Let's start by understanding what exactly volume rendering is in the case of translucent materials such as this cloud. If we look closely at it, we see that it's made up of a huge number of microscopic water droplet particles. There's so many of them that in almost all cases, modeling their exact geometry is too computationally expensive. We instead model only the expected locations of these particles, which gives us a stochastic representation of the microparticle geometry in the form of a particle density. The particle density representation allows us to trace light paths through the cloud without knowing the exact particle locations. To achieve this, the only thing we need to know is the distance a light ray travels before first encountering the cloud geometry. In the deterministic representation, this distance is simply the deterministic distance to the first intersection of the particle. Different configurations of particles lead to varying intersection distances. In the stochastic representation, we account for this variability by using the distribution of these distance values, or free flight distribution, across all possible random configurations. Amazingly, this distribution has a known closed form as an exponential. Then, rather than use an intersection with a single particle configuration, volume rendering averages over distance values from this distribution. Let's now consider an opaque solid such as the Lego truck. We represent the Lego truck using a binary vacancy, which equals 1 in the exterior and 0 in the interior of the truck. During reconstruction, we don't know the binary vacancy exactly, as there's uncertainty about which regions of space are vacant. We can manage this uncertainty using volume rendering by working out an appropriate stochastic geometry representation and a corresponding free flight distribution. As in the microparticle case, our stochastic representation is the expected value of the binary vacancy, which is a probabilistic non-binary vacancy. As for the free flight distribution, we note that in the deterministic case, an intersection happens at a point along the ray where the vacancy transitions from 1 to 0. Thus, the free flight distribution is the probability that the first such transition happens at any given distance along the ray. Our key technical contribution is to derive a closed form expression for the free flight distribution for stochastic opaque solids. We do so using the theory of continuous time Markov processes. In our context, Markovianity means that the probability of first intersection along a ray is independent of the past history of the ray. We prove that the free flight distribution for stochastic opaque solids is exponential, just as in the classical case of translucency. We also prove that the attenuation coefficient of this exponential equals a simple function of the probabilistic vacancy and its gradient. Our paper provides a rigorous proof which relies on the Kolmogorov equations from Markov processes and reciprocity constraints from physics. Lastly, we draw connections with microflake models in rendering and generalize this attenuation coefficient to account for the ambiguity in normal directions towards the interior of an opaque solid. Our theory provides stochastic geometric interpretations of volume rendering of neural implicit and point cloud representations, both of which we can use to parameterize a probabilistic vacancy. Lastly, our theory allows us to achieve improved surface reconstruction performance compared to several recent works across a variety of datasets. Our project website has a full interactive visualization of these results alongside our code.